Hi, I'm Renan Medina, and we represent the Research and Development section of Dell Incorporated, which is a computer company. We are assigned the task of separating the electrical components of a typical Dell motherboard. Now we're going to introduce ourselves. Me Renan Medina, as you know already, and I basically was a project manager. I was influential in identifying user requirements and doing the functional analysis of the machine.
Good afternoon. My name is Samuel Alexander, and I was responsible for the three conceptual designs, giving a brief description about how these conceptual designs fulfill the user requirements.
Hi, my name is Tara Nurse, and for this group, I was responsible for gathering the background information, and that is the literary articles and the patent reviews. These
Present today, my name is Charles Samuel, and I was responsible for developing the general introduction for our project. This
My name is Charles Samuel, and today I'll be talking about the introduction, and this entails the background, the aim, the statement of problem, and the objectives. In this section, we'll discuss the background of PCBs, and this entails the history, construction, and recycling of circuit board technology. Computers of previous times were comprised of huge machines that were not as powerful as the ones we have today. Now they are smaller but yet more powerful computer systems due to the implementation of printed circuit board technology. The usefulness of the PCB grew over time as it mechanically supports and electronically connects electric components using conductive tracks, pads, and other features from one or more sheets of copper. A significant advancement was the development of wire wrapping, where a small gauge is literally wrapped around a post at each connection point to create a gas-tight connection, which is highly ductile and easy to change. After the process of creation of a PCB, excess materials may be wasted due to the increase in the demand of electronics over the years, and this can lead to toxic waste to any environment. With this being said, a recycling plant should be established as a means of reusing useful materials while decreasing the rate of pollution. Some recycling methods that can be used as a means of extrusion are pyrometallurgy, combustion, electrolysis, sharp separation, and jigging. Now we shall discuss the statement of problem. Computer motherboards are a very rich source of valuable precious metals and rare earth metals. Motherboards are usually recycled by crushing and smelting. However, this extracts only a few precious metals, wasting much of the other valuable resources such as rare earth metal, which include gold, silver, platinum, and others. Being part of the research and development section of Dell Incorporated, a computer company, it is required for us to design a process that separates the components and solder from the effective motherboards. The aim of our project is to design a manufacturing process that disassembles and separates the components and solder of defective motherboards in a safe, environmentally friendly, and effective way. Now we shall point out the objectives of this project. To research and review fundamentals and pertinent contextual background information on printed circuit board. To define the problem. To review pertinent literatures and patents surrounding AIM. To identify and prioritize user requirements, to develop design specifications based on user requirements, to develop a functional breakdown of machine, to identify possible ways of performing functions developed, to generate alternative designs of machine, to analyze and select a design based on satisfaction of prioritized user requirements, and to describe the final design.
Our aim was to design a machine that effectively and efficiently separates solder and components from circuit boards. The information used was gathered from various peer-reviewed articles and patents. The article, Recycle Technology for Recovering Resources and Products from Waste Printed Circuit Boards, outlines quantities of precious metals to be gained from recycling PCBs. It states that PCBs contain almost 28% of metals, which are abundant non-ferrous metals, and the purity of these metals can be as much as 10 times higher than rich content minerals. PCBs are recycled not only to reclaim those precious metals, but also because of the harm they cause to the environment when improperly dumped, such as leaching toxins into groundwater and dioxins into the air. Methods currently used to recycle them are pyrometallurgy, jigging, density-based separation, and electrolysis. The article, Apparatus for Electronic Component Disassembly from Printed Circuit Board Assembly in E-Waste, discussed a machine used that remove components from PCB with principles our group can benefit from. The machine highlighted in this article uses a series of rollers and steel brushes to crush the components and sweep them off the circuit board into a collection system. As the motherboards are fed into the machine, they are heated by infrared rays at a temperature that liquefies the solder. The data collected from this test revealed that at a feed rate of 1 centimeter per second and 250 degrees Celsius, there was 94% component removal. The first patent is a method for printed circuit board and printed wiring board cleaning. Without negatively affecting the component of the PCB or the board itself, it safely and effectively removes rosin soldering fluxes. Additionally, methods on composition to detect improperly cured UV solder mask, which greatly reduces premature circuit failure. The key component of the composition is terpene, which is characterized by its low toxicity, high biodegradability, and non-corrosiveness. It has the ability to remove rosin solder flux, oils, waxes, greases, and adhesive tape residues. When combined with emulsifiers, removal by water is possible. The second patent is a portable electric hot air rework tool for soldering and desoldering printed circuit assemblies. This tool directs hot air or steam onto a component or a localized area with soldered material. Components include an air plenum, which contains the heater and turbulators for creating turbulent heated air, a blower, a PC assembly support grid, controls, orifice indicator, and a base plate. A heat-sensitive lacquer with known melting point is placed on the component or desired location, and when melted with the tool, components can be removed or added. The final patent is a desoldering hot plate. It is meant to remove and replace large and small multi-pin devices with only simple changes. A large area, shallow solder pot is provided that has the ability to catch overflow. Masks are provided to be attached to the bottom side of a PCB to expose the pins of the device to be removed. This is then placed on top of the solder pot to melt the solder. The device is removed, and to replace it, solder is melted into the free holes, and the new device is attached. Problems such as icicling and bridging can be eliminated by using commercial soldering oil and flux.
Hi, my name is René Medina, and I will continue with the problem definition. This entails the user requirements, pairwise comparison chart, relative weightings, design requirements, and objectives and metrics. We work in the R&D department in Dell, thus we are our own user and client. As a team, we came up with user requirements and categorize them into design attributes. These attributes include efficiency, in terms of being functionally effective, cost effective, time effective, and material effective. We also considered safety, maintenance, user friendliness, and environmental impact. Next, we look at the pairwise comparison chart. Using the pairwise comparison method, these attributes were prioritized in order using the relative weightings process. This was done by comparing attributes. For example, efficiency on the first column, second row, was compared to safety, the first column, third row, where we decided that safety was more important. We continued this process for the other attributes. However, we found that the attribute easy to maintain was given a 0, so the 2x plus 1 algorithm was applied. We total the 2x plus 1 column, and this percentage represents the prioritized attributes, which we call the relative weighted. The following table represents prioritized attributes, where the relative weighting showed that safety was most important and easy to maintain was the least. So we move on to the design requirements, where the attributes is a qualitative representation of what the user wants. To make these attributes a reality, we as an engineering team converted these qualitative representations to quantitative representation of what the user wants. The design requirement is a list of requirements the design should and must have. For example, since safety is the highest user requirement, the moving parts of the machine must be safe. Now you all can look at the other design requirements our team came up with in order to fulfill the user requirements. Now we move on to the objectives and metrics section. Objectives and metrics is a metric system applied to the attributes showing possible ways the outcome can occur. In our objectives and metrics table, 3 possible outcomes of the attributes are generated, and the metric system is a way of how much the objectives satisfy the design specification. In the table, 1 represents that the objective does not satisfy the design specification, 2 is that it intermediately satisfies the design specification, and 3 is that it totally satisfies the design specification. So for instance, 1 is given to all moving parts are fully exposed in the design specification of safety. 2 is given to a few moving parts are exposed, and 3 is given to no moving parts are exposed. Now you can pause the video at the relative time frames, looking at the objectives and the metric systems applied to the various attributes. So I, Renan Medina, will discuss now the functional analysis of the machine, and I'll do this using the black box method and a functional decomposition chart, as well as a morphological chart. The primary function of the machine is to separate the solder and components from a motherboard. In order to achieve this primary function, we must have energy inputs, whether the energy input be electrical, human, heat, mechanical, or obviously put in the motherboard itself. We must insert this into the system in order to achieve this primary function. We can also control these energy inputs, and that's where the information input comes. So if we was to heat the solder, we would have an energy input of what temperature it must be at. And from the literature review, we found that the ideal was 250 degrees Celsius. Lastly, we will obviously have outputs. We have the desired outputs, or the products we actually want, which is the separated solder, the electrical components, and the boards. We will have byproducts, energies that are dissipated in other forms, which is heat, sound, and mechanical vibrations. And I know it's not shown in this diagram, but we can also have an information output, which, for example, could count the amount of boards passed, or the electrical components, or the volume of solder. So in order to achieve the primary function, we need to decompose it into a list of sub-functions, moving in a particular order to achieve the primary functions. This includes the loading of the motherboard into the process itself, heat energy, if used, or chemical energy, if used, removal of the solder, removal of components, drying mechanism if chemical sub-function is used, and unloading of components separately. So the following figure shows a more detailed functional breakdown of where the relative inputs are applied to the sub-functions to achieve the primary function of the manufacturing process. Blue represents inputs, black represents information inputs or outputs, which is basically the settings applied to the energy inputs. Green represents the main processes, which are obviously the sub-functions in a particular order, and red represents the outputs. So for example, for heat or chemical energy, the energy input is electrical energy is transferred to heat or chemical energy, and well, in order to control this energy input, information input is necessary, where the signal set is controlling the temperature or concentration of the mechanism applied. The morphological chart is a representation of our team coming together, brainstorming, and generating multiple ways of performing the sub-function shown. This process is influential in that it serves as an option source to achieve sub-functions for the conceptual design. So, for example, the movement of motherboard's row, we can do this using rollers, conveyors, gravity, or manually.
Hello, my name is Samuel Alexander, and I'll be giving the conceptual design descriptions. Some of our conceptual designs involve a chemical pre-process. This chemical pre-process dissolves the solder into an aqueous state. The chemical used, terpene, is biodegradable and does not cause damage to skin when it is in direct contact. The process begins with loading the cylindrical drum with motherboards and locking them in so they don't fall out when the drum rotates. A hydraulic bin lifts the surround the drum, after which the bin can be filled with terpene until it submerges the drum. The submerged drum then rotates in the liquid as a means of speeding up the chemical reaction through agitation. When the chemical process is complete, the bin is drained of liquid, after which it descends so the motherboards can be accessed. Using this method allows for many motherboards to be done at the same time and is an additional advantage when designing a manufacturing process for our client. The first conceptual design is split into two parts, a chemical process, which was described earlier, and a mechanical process. Once the chemical process is complete, the mechanical process can begin. A set of vertically oriented rollers feed the boards towards a curved pair of blades. The rollers themselves converge slightly as they approach the blades, gradually applying a clamping force to hold the motherboard. As the boards are fed through the machine, the sharp edge of the blades cut the electrical components off the circuit board. The space between the blades allowed the wafer-like PCBs to pass through while collecting the other components. The components are then vacuumed through chambers near the blades and into collecting bins on either side of the machine. These can be detached when necessary. The machine also has an emergency stop in the eventuality that some incident were to occur. The second conceptual design also starts with a chemical pre-process to remove solder, but comes with some major differences in methods along the way. After the pre-processing stage, the motherboards are fed into the machine via vertically oriented rollers, which gradually clamp the boards. As the boards are fed through the machine, rotary steel brushes scrub the electrical components off the board by abrasive action. The dislodged components, some of which may be flung onto the walls of the machine, fall into a collecting tray below. The electrical components can then be collected in the tray for future recycling. The fiberglass reinforced PCBs are fed out on the other side of the machine, where they can be manually collected and stored for recycling. There is an emergency stop that can easily be accessed. The third conceptual design takes a different approach to motherboard disassembly. Rather than chemically removing the solder, infrared heaters are used to melt the solder in a fully enclosed chamber. The hydraulic system shown above acts to close and open the chamber as part of the machine's operation. Motherboards feed to and from the machine in oriented pairs via a conveyor belt until they align on either side of the chamber for processing. The top hatch closes hydraulically, both to clamp the boards and to seal the chamber. The sealed chamber, unlike the other two conceptual designs, minimize heat losses if heating were to occur. The solder on the motherboard melts and drips into containers at the bottom of the machine. After this process, the electrical components are vacuumed up the top half of the machine through flexible pipes and are collected in an awaiting chamber. The top of the machine then returns to atmospheric pressure by allowing air back into the chamber. It then lifts to allow the cleared PCBs to roll off the machine for collection. The machine also has an emergency stop system.
Now that all the conceptual designs are developed, using the weighted attributes and the objectives and metrics system, we as engineers came together and graded the conceptual designs in terms of how much the design satisfies the design specifications. From our discussion, design 1 scored the highest. This is because the chemical process makes it safer for humans and the environment because no toxic fumes are produced compared to when heating solder. Also, the machine has no moving parts. It is cost effective because the cost of buying terpene emulsificants is cheaper than heating solder at 250 degrees Celsius. Also, it is time efficient because more boards can be processed at a time compared to the heating method where the feed rate should be 1 centimeter per second as discussed in the literature review.
From the results of the selection matrix, Concept 1 was chosen as the best manufacturing process that would satisfy our clients' needs. The final design would have some additional improvements to the original Concept 1, in that the blades, rollers, and inner walls of the machine can be electroplated with stainless steel to make it more corrosion resistant. The contact surface of the rollers would be covered with polyurethane rubber to avoid slipping between the rollers and the motherboard. A 3-phase brushless DC motor with an included inverter will be used to drive the system of rollers in the machine. A control system would also be attached so that the feed rates can be adjusted if desired. For our vacuum source, we will be using a rotary vane pump because of its power and reliability. Chain link rollers will be used to connect the motor to the rollers of the machine to ensure a consistent supply of power. Pillow block bearings will be used to reduce friction between the shaft rollers and their supports. The final design will also include hinge panel sides that can be unlocked to open the chamber for cleaning and maintenance. The bins on the sides of the machine will be detachable, so the electrical components can easily be collected. For the last stage of the process, a bin will be placed at the end of the machine so that the exiting circuit boards can be collected.